Hey, hi everybody. I hope everybody's doing great. Very good evening. I see a lot of people here. Right. Okay. Right. I think this is the first chemistry class in the sense for this course, right? For the kind of a crash course, the test series, however you want to call it. Right. So learning room. Good evening. Good evening, Kaushik. Right. So it's good to be with all of you after a long time. Right. I know. I think few of them. Yeah. I think so many of them. I know if you just look at the names, I've not seen their faces because it's completely online. But yeah, most of you, I think we have had classes, right? I have been handling the 11th class for you. Anyways, so enough being said. So straight away go into today's work, right? And the assigned work is haloalkanes, haloarenes, right? We have to revise haloalkanes and haloarenes organic chapter, right? Fine. So I don't know whether you have understood how this particular course is going to work for you, right? So we'll not be teaching as such, right? Whatever in the schedule you see that some particular chapters given to you, that is not going to be taught, right? So how are we going to go about it is, say we'll be taking up questions, right? We have a set of questions we like for me to discuss with you, right? So it is going to be kind of interaction where we'll be solving questions wherever you don't know that concept. I'll teach you, and eventually you'll get to know the concept. Eventually, how many times you'll learn the same thing? How many times will hear someone saying that this is the concept? Right now, it is time to move on and actually see how do you approach examinations. Right? How do you answer questions? That is what is going to be more important. Right? That is the entire agenda of the entire course. Right? So to make you good at doing examination. Right? Concept obviously you should know. Without that, exam doing well is not going to be possible, right? Okay, so if at all you have any doubts, even though the crowd is very large, you can always stop me right there and ask, right? I don't think I'll be able to see your chats. I think I'll be able to see also, no problem. But I would prefer if you can just unmute yourself and ask what exactly is the doubt, or you understand. If you want me to repeat anything, if you don't understand what something I'm writing, right? Anything for that matter, you can always stop me right there and ask, right? Okay, fine. Let me share my screen. Yeah. Haloalkanes and haloarenes. This is the one. Right. So yeah, as I said, the chapter is going to be haloalkanes, haloarenes, and we'll be solving right away questions, how to approach the questions, and all those the concepts we'll see, right? And it's not like straight away I'll give you the answer. Okay, I'll give you some time, maybe 1 or 2 minutes for you to think about the concept. How can you write this, right? Anybody's interested, again you can answer, right? There is no stopping you there. Okay, right. Just a moment. Okay, right. Now this is the question. Is everybody able to see my screen? Is everything clear?
Yes, sir.
Okay, right. What happened? Why is it not coming? Oh, it's coming. Okay. I want a lighter pen. 1 second. Okay, right. So the question is the IUPAC name of the compound shown below is, right? This is the compound given to you, right? You have to write the IUPAC names, right? Fine. Now it's all about priorities, right? If I'm having this particular compound, Br and Cl, now we have 3 things to look for. What are the 3 things to look for? We have chlorine, we have double bond, and we have bromine, right? Now, out of all these things, which is going to have the maximum priority? And obviously, whichever is going to have maximum priority, that particular group should have the least possible locant. When I say locant, it is the number. Yeah, tell me the answer. Which is going to be the highest priority?
The double bond.
Double bond, absolutely. Right? It is neither chlorine nor bromine. It is the double bond which should be given the maximum priority. Okay, right? So you don't have any place to start rather than putting either 1 here or 1 here. You can only do that, right? If you put 1 here, right? If you put 1 here, can I put 2 here? Can I?
No, sir.
Why?
Sir, because we are supposed to go along the double bond.
That's good. That's good. Still, you remember stuff. Good. So once you put, what I'm trying to say is that if you put 1 here, you have to mandatorily put 2 here. You cannot just miss the start of the double bond, you have to finish the double bond. You have to travel the double bond completely. Then only go to the other things, right? That means putting 2 here is absolutely not okay, right? Again, if you put 1 here, you have to put 2 here. There is no other way. There is no that you can put 1 here and 2 here. That absolutely is nonsense. That you cannot do. Okay, right. I need still a little thicker. Okay, I think this will be better. Right. Anyways, now how you should, now again I'll draw. Okay, again I'll draw my diagram. Right. So we have this one with this one and this one. So we understood double bond is going to have the maximum priority. Is it not? Right. Now among chlorine and bromine, which is going to have maximum priority?
Bromine.
It is now based on your atomic numbers or atomic masses, right? Bromine is heavier, so that is going to be given more priority. Okay, but you have to first give the priority to your double bond only. So either 1 here or 1 here, as we already spoke. And the better way is that you will put 1 here and 2 here. Why? Because if you had put 1 here, what would have been the number you would have gotten for BR? Would have been 6. Is it not? I hope everybody is able to follow, right? If I put 1 here, 2, 3, 4, 5, 6, right? 6th position will get BR, and that is not right. Is it not? Among chlorine and bromine, bromine has to get the least possible number. I mean, after double bond, obviously, right? So the correct way to put everything is like this: 1, 2, 3, 4, 5, 6. This is how we'll number the carbon atoms. Now, once the numbering is done, the naming is very easy. It's all about numbering, right? Okay. So now, how do we name this? Obviously, this is going to be a side. Now we're going to call it as normal hex. This is cyclohex, right? And in the first position, we have a double bond, 1-ene, or you can just write hexene. That is also okay, right? And in the third position, we have Br. In the first position, we have chloro. So if we are going to write fluoro and bromo, yes. But any order should I specifically follow? Alphabetical. Exactly. Whenever we talk about prefixes, we have to follow your alphabetical order. That is, your CL, BR comes first alphabetically. Not because it is having more priority. Remember that. Whenever the priority is only for numbering, right? Now, when you write the name, there the alphabetical order matters, right? So you should write it as 3 bromo, right, and 1 chloro, cyclohexene. So where is it? 3 bromo, 1 chloro, cyclohexene is right here, right? Option C should be the answer, right? Okay. Yeah, the answer is not given, but the answer is 3. Okay, 3 bromo, cyclohexene. Sorry, 3 bromo, 1 chloro, cyclohexene. Okay, right. Moving on. Right. The reaction between hydrogen bromide with propene in the absence of peroxide is an example for what? First of all, forget about free radical. First, okay, if I ask you.
So nucleophilic addition.
Nucleophilic addition. Fine. Let us take a guess, right? I want everybody to go to the chat box, right, and type your answers. Like, it doesn't matter whether you're right or wrong, right? We'll just see, how you're participating, right? How you're thinking. That's all it is. Go on. Maybe I'll close this again. Nobody want to answer. Okay, one answer. Okay. Nucleophilic addition. Okay, electrophilic substitution. Nucleophilic addition. Okay, guys, how do you understand this? Okay, one more. Option B. Okay. Right. Anyways, now how do you approach this? Right. See, please understand. First of all, when I'm going to have some kind of unsaturation, right? Everybody says nucleophilic addition. Fine. Okay. Right. Okay. So when I'm going to have any kind of unsaturation, that is, say I have a C double bond C, right? And I add something to get 2 more bonds like this, like this. This is some A, B, something like that, right? Or another case of addition reaction is there. We can have C double bond, though that is also double bond unsaturation. Now, if you add AB, say in this case, you will get oxygen having A and carbon having A and oxygen having B, something like that, right? First of all these are addition reactions. That's the first thing, right? It is never, there is definitely not a substitution reaction. So this can definitely be chucked out. Is it not? It is not a substitution reaction for sure. Substitution is where one functional group is replaced with another functional group. Say Cl replacing with OH, OH replacing with Cl. All those are examples of substitution reactions, right? Fine. Now, what about the addition reaction? Now, addition reactions can be of three types, right? One is three things are given there: free radical addition, nucleophilic addition, electrophilic addition, right? And it's not like all the types of bonds. Say whether if I'm going to have C double bond C, right? If I'm going to have C double bond C, it's not like C double bond C will take up both free radical as well as nucleophile as well as electrophile. Same goes to C double bond though. It's not like everything will be able to perform everything. No, right? All there's going to be some logic, right? Now we'll try to understand that, right? So now, if you are going to have a C double bond C, right? Now, what you understand is that this pi cloud, which is here, I'm highlighting it, right? This pi cloud, which is here, is having very high electron density. Is it not? This pi cloud, which is here, is having very high electron density. So it is always in loop for some kind of positive charges. Okay, this particular compound, right, is always in search for some kind of positive charge because this pi cloud is having very high electron density. Right? So because of what is going to happen, now if you put an electrophile that is having a positive charge, electrophiles are positively charged, nucleophiles are negatively charged, right? So now what is going to happen is this pi cloud is going to go and get attracted to this electrophile, right? Now, if you want to properly understand what exactly is happening, I'll be able to explain you like this. Say I have an electrophile like this. Now, this bond carbon, this pi bond is going to undergo heterolytic cleavage. You know what heterolytic cleavage is? That means these two electrons are given to this carbon. Okay, so now this carbon is going to have a negative charge. That negatively charged carbon goes and attacks your electrophile, which is having a positive charge. Right? And in that process, what is going to happen? In that process, we are going to have C. And what happened to this C? This C has lost electron, right? Is it not? It had one electron before in the form of a bond, and that electron is lost. So this carbon is going to get a positive charge, right? Next, now you see that this had already two bonds, and now you see that one more electrophile is also going to come to this, right? Now this is the first step in the addition reaction for alkenes, or in case of any C double bonds, or C triple bonds also. Okay, right. Next, what is going to happen? Now, if at all you have any negative charge, nucleophile, that is going to come and attack your positive charge, the carbon. So you will get nucleophile here and you will get electrophile here. Now, there's a confusion, right? Besides electrophilic addition, okay, electrophile is getting added, right? And in the next step, we are seeing that nucleophile is also getting added. So what is this? Whether it's a nucleophilic addition or electrophilic addition, right? Now, all you have to understand is that whichever happens first, that is what you consider. That is, in this reaction, in this kind of a mechanism that you see, that is the electrophile, that is positively charged species, that is the one attacking first, right? So we will call this kind of addition reactions as electrophilic addition reactions because it's electrophile is attacks first, right? Okay, fine. Now, what about other case? Let me make a new page. Okay, fine. So if I take, for example, C double bond is there. Now I'm going for an aldehyde or ketone, for example. Right? Now what happens is you see that this particular pi cloud is there. That's okay, right? But this bond is polar, right? This C double bond O is very highly polar because oxygen is very highly electronegative and carbon is not so electronegative. Is it not? Right? So what is going to happen? You will see that since oxygen is more electronegative, the electron cloud, which is here in the form of sigma bonds and pi bonds, are going to move towards oxygen. Is it not? Are going to be more towards oxygen. right? So now oxygen is going to have a partial negative charge, right? And whereas this carbon, from the carbon, the electron cloud is moving away from carbon. The electron cloud moves in this direction. Okay, so because of that, you will see that carbon is going to have a partial positive charge, right? Now, if you understand this point, then you can easily understand that it is going to be first the nucleophile which will come and attack this positively charged carbon. And in that process, this bond breaks, right? And in that process, this bond breaks, right? So what is going to be the product now? We will get this carbon having the nucleophile, and this oxygen bond is broken and given to oxygen, you are finding a negative charge. And obviously, this will be able to take up any kind of electrophile which is there in the system to form C, Nu, O, E. O is the electron, E is the electrophile. Something like that. If it is H plus, then it is E plus, something like that. Okay. Right. So now you see that it is the nucleophiles attacking first. So we will call this one as nucleophilic addition reactions. So your aldehydes and ketones will always undergo nucleophilic addition, whereas your alkenes and alkynes will undergo always electrophilic addition reactions.
Sir,
Yes.
sir, if an electrophile attacks first, then again this will be electrophilic addition, sir.
Yes.
This is happening because
in this case,
nucleophile.
exactly. In this case, electrophile can never attack first.
Okay, sir.
Right. Okay. It is always going to be the nucleophile. Right. Okay. So now there is another case. Right. When can we have free radical addition? That's another question, is it not? Till now, we saw electrophilic addition happening in case of alkenes, alkynes, nucleophilic addition in case of your aldehydes and ketones having C double bond O. Right. What about your, what is that? Free radical addition. Right. Now that happens when you have this particular reaction. Say if I have CH3, CH, double bond, CH2. Now if I put HBr in the presence of peroxide, we know what happens. Anti-Markovnikov addition happens. Right? Markovnikov addition is where Br will go here. Anti-Markovnikov is where Br will come here. Right? It is because the entire mechanism is very different. Right? We'll see both the mechanism maybe. Okay. Right. So now you will see that I'm going to have CH3. Okay. Okay. The product formed is going to be CH3, CH2, and CH2 and Br. You see the anti-Markovnikov addition. Br is going to attack in the last, like this is a less substitute position. Okay. Right. Fine. Now what is the mechanism for this? Right. That is where it comes. You don't know the mechanism. The mechanism is not given in a textbook, but this is a beautiful example for free radical addition. Right. So fine. They can waste some time on this. It's very interesting. Okay. Fine. This is what happens. So now you will see. Okay. First, what happens is your peroxide. Right. Now this peroxide, for example, say I take hydrogen peroxide. Okay. Hydrogen peroxide formula is H2O2. Okay. So first, this H2O2. This is how it looks. Hydrogen peroxide undergoes homolytic cleavage. This is how I represent it. If it is heterolytic cleavage, I'll put a single arrow towards one of the atom. If it is homolytic cleavage, I will use this half arrows on both the sides. Okay. So now this is going to produce, can I say, two OH radicals. This dot represents that this electron is going back to oxygen and this electron is going back to this oxygen. Right. So you'll form two OH dots. Okay. Now what is going to happen is this OH dot, right, is going to react with HBr. Now this OH dot is going to be very unstable. Is it not? This OH dot is going to be very unstable. Right. So now what is going to happen is that this OH dot is going to abstract a H dot from this. Okay. This OH dot is going to abstract a H dot from this. So you will form H2O. Obviously H and OH will combine together to form H2O. Right. And what is left out from HBr is this Br dot, bromine free radical. Right. Okay. Continuing. Okay. Right. Now we just go back and see what happens. So now first step was this H2O2 undergoing homolytic cleavage to hydroxyl radical, the OH radical. Right. And this OH radical is very unstable. So from the HBr, it is going to take a H dot forming Br dot. Okay. Next step is where the alkene comes. CH3, CH double bond CH2. Now comes your Br dot. Okay. Right. Now, obviously, this pi bond has to undergo homolytic cleavage. Okay, this pi bond has to undergo homolytic cleavage. Correct. Now, obviously, wherever the bromine atom is going to attack, or not, I should not say call it as an atom, wherever the bromine radical is going to go and attack whichever carbon, the other carbon is going to still have the free radical. I hope you're able to get the point. Right? If, for example, this radical is getting formed here, this radical is getting formed here. If this radical and this radical comes together to make a bond, there will be still radical present on this carbon. Actually, we'll write both the possibilities. Br dot, Br dot. One possibility is Br dot getting attacked here. Right? That is, you will form CH3 CH dot CH2Br. The radical is here. Another possibility is that this Br going to attacking this carbon. So you will form CH3 CHBr CH2 dot. The radical is now here. Right? Now, what kind of radical these two are? Can you tell me what kind of radical the first one is?
2 degree.
Second degree, or it is called as a secondary free radical. Okay, now what about this one?
Primary.
Primary, because you see that this radical attached to only one other carbon atom. Right? Okay, fine. So this is a 2 degree radical, this is a 1 degree radical, which is more stable.
Secondary.
Secondary. The order of stability of free radical is this: tertiary more stable than secondary, secondary more stable than primary. Again, the reasons for that, I'm going to go into the reasons. Right? Tertiary radical is more stable than secondary, secondary is more stable than primary. So definitely, this is what is going to be formed in major amounts. Right? So where are you seeing now the Br is getting attacked? The Br, if it is attacking the unsubstituted position, that is anti-Markovnikov's position, then only you are able to form a stable free radical. Right? And eventually they will take up a H dot, right? And they are eventually going to form CH3, CH2, CH2, Br. Okay? So that is the reason why you're going for anti-Markovnikov solution, because it is going to be a free radical addition. Right? If it was a normal thing, right? If it was your CH is the same molecule, actually, we'll take it here. Same molecule is there, that is CH3, CH double bond CH2 with your HBr alone, I'll take. Right? Now you see that there is H plus also, Br minus also. Now what comes first? Obviously, this is an electrophilic addition. So H plus has to come first. Yeah, primary free radical. Okay. Right? So it is obviously going to be your H plus which has to come first. Right? Again, there are going to be two possibilities. Right? How the bond can break and which carbon atom is going to take up the H plus matters. Right? For example, if I break this bond like this and this comes and takes up the H plus, then what will happen? You will see that this carbon has lost electron. This carbon has lost electron. So you will form CH3, CH plus CH3. Right? Another possibility is, we'll write it again, CH3, CH double bond CH2, and you're seeing that coming H plus. Okay. Now this bond is going to break like this, that is towards this carbon, and this goes and attacks this hydrogen plus. So now what will you have? You will have CH3, CH2, and this carbon has now lost electron. So you will form CH3, CH2 plus. Again, for the same logic, secondary carbocation, this thing is there. Primary carbocation is there. Secondary carbocation is there. So definitely, I know the order of stability is tertiary greater than secondary greater than primary. For free radicals and your what is that? Your carbocations, you use the same order. But for carbanions, it's exactly opposite. Okay, for free radicals and carbocations, same thing. Okay, fine. So definitely we know state. The tertiary is more stable. So now what is going to happen? Now comes your nucleophile, that is your Br minus, which is there here. Right? Now that is going to come and attack here, and you're going to form your Markovnikov's product. CH3, CH, Br, CH3. It's because the entire mechanisms are very different. Right? These are not the simple questions you cannot miss. Right? C double bond is electrophilic addition. C double bond C with the presence of HBr and peroxide is going to be a free radical addition. C double bond O's will undergo nucleophilic addition. Now you understood the logic also behind it. There's no need to cram anything here. Cram anything up. No need to mug up. Okay. Any questions anybody has? Okay, I hope you guys are following. Right. Next. So the answer we didn't mark. So okay, we did miss this question also. Okay, great. Yeah. So the answer for this question, the reaction of hydrogen bromide in the presence of propene in the absence of peroxide is definitely going to be an electrophilic addition. D is the answer. Right. Next. Fine. When hydrochloric gas is heated with propene in the absence of benzoyl peroxide, obviously in the absence of peroxide, now it is going to be Markovnikov's product, is it not? Right? So we have propene, we know what is the product now. If it is propene, Markovnikov's product, this is what you will get. Right? So you'll get what? 2, this is your second position, 2-chloropropane. A is the answer. Very simple. Right? Okay. Yes, 2-chloropropane only. Absolutely. Okay, next.
Sir.
Addition of
Sir, can you go to that question?
Sir, but it's in the presence of benzoyl peroxide, bro. So it should
Oh, I'm sorry. I read the question wrongly. Yes, it's in the presence of benzoyl peroxide. Obviously, this is not the answer then. Right? Now,
Sir, so N-propyl chloride is
yeah, CH2Br. This is what you will get. So that is N-propyl chloride. I'm sorry. Yes, that's true. That's very true. Right? Only in the absence of peroxide is anti-Markovnikov because, sorry, absence of peroxide is Markovnikov's, presence of peroxide it is anti-Markovnikov's. Right? Okay. Right. Next. Addition of HBr gives the same product in the presence and in the absence of peroxide when the alkene is. It's very simple. Now, anti-Markovnikov's product and the Markovnikov's product, when it can be same, if you can just think about it logically, when you see that the alkene is going to be symmetrical, doesn't matter where I put the Br, still it is going to have the same name, right? Now that is going to definitely have a case where it doesn't matter whether it is going to be anti-Markovnikov's or Markovnikov's, right? So that's what you have to check for. For example, how you will check for this question, say for example, if you take one butene, CH3, CH double bond, CH, CH2, CH3. Now if you add Br here, that is position number 1. If you add Br here, this is position number 2. So the name changes. That means they're 2 different compounds. Okay. Whenever the number changes, then in the name, IUPAC name, that means they are 2 different compounds. Okay. Next, 2-methyl. Okay, I think someone is saying the answer. Okay. 2-methyl propene. Okay, this is what is 2-methyl propene, right? Again, this is position number 1 if you add the Br here. This is position number 2 if you add the Br here. So again, 2 different compounds, right? Propene, we already know, again, it is going to become 1 or 2. So obviously the answer is going to be butene. We'll see how, right? CH3, CH double bond CH, CH3, right? Now, if you add Br here, that becomes position number 2, right? And if you add Br here, the position number becomes 3. No, you see that you start numbering from here, you'll put 2 here. So either way, if you add, it is actually going to be 2-bromo-butane. That's what is going to happen, right? Whether it is going to be Markovnikov's or anti-Markovnikov's, right? So the answer is going to be 2-butene or butene, whatever it is. Okay, right. Moving on. The addition of HBr is easiest in. Now look at this. Addition of HBr is going to be easiest in. How do you understand this question? Right? Now, definitely, these kind of things, if they ask you addition of HBr in the absence of peroxide, obviously, we're talking about addition of HBr in the absence of peroxide, right? Now, all that you have to understand is that you are seeing that the intermediate, we saw the mechanism, right? We saw the mechanism where the electrophile attacks, what happens, the carbon is going to have a positive charge, right? So the intermediate formed is actually a carbocation, right? So now, how do you approach these kind of questions is that or if they ask about reactivity or if they ask about the ability to undergo, so whatever be the case, right? All you have to understand is that if there is whatever is the intermediate, more and more stable, the intermediate is, stability of the intermediate, more and more is the reactivity. Now, why am I saying this? For example, if I can have some particular compound which will be able to form a very, very, very stable carbocation, and that carbocation form can be formed very easily, is it not? Right? More and more stable the carbocation is, more and more easily or quickly I'll be able to form the reaction. I mean, I'll be able to form the carbocation, more and more stable it is. And obviously, that carbocation will become the majority, it will going to become faster, and the nucleophile can attack. And then that particular product will be the fastest or the more major product. Right? Okay. Now, if you check in any of these, right? Say, for example, if you break the bond and put a positive charge here, there is an electron withdrawing group here, right? Electron withdrawing group, Cl is electron withdrawing group, which is already, this is already having lesser number of electrons here. Because of chlorine, now you will see that the positive charge will still keeping on increasing, right? We need to have less positive charge. Okay, how do you compare stabilities? More and more neutral it is, more and more is the stability. Is it not? Right? So now you see that the positive charge is increasing because of the presence of chlorine. Right? Now here you have two chlorine atoms, still worse, right? And in this case, this is okay, right? This will be able to form a carbocation. A secondary carbocation is formed, and this two sides we have methyl groups, electron donating group. So you can expect that here the positive charge will decrease. So it is more stable. Okay. Let us check for the last one also, right? If I have the, obviously this is going to become primary carbocation, doesn't matter, but the other one, this will form a tertiary carbocation. Is it not? This carbon is attached to 2 methyl groups, and one more methyl group will be there because we added H plus. Is it not? Now this is going to form a tertiary carbocation. So obviously this carbocation is the most stable one and which can be formed the most easily, and that's why this particular reaction will be happening the fastest. Right? So the answer to this question is again going to be D, because of stability of carbocation. Right? Okay. Fine. Next, a compound is formed by substitution of 2 chlorine atoms for 2 hydrogen atoms in propane. The number of possible isomeric compounds is. Right? Now they're asking that. First, another question properly. Right? They're telling a compound is formed by substitution of 2 chlorine for 2 hydrogens in propane. That means what? I have CH3, CH2, CH3. Right? Now that is getting converted into, there are going to be so many hydrogens here. Any 2 of the hydrogen is replaced with 2 chlorine atoms. Okay? Any one of these hydrogen atom, any 2 of these hydrogen atoms are going to get replaced with chlorine atoms. Okay? Now, what are the possibilities is what they're asking. Where and all the chlorine can go, and different places chlorine can go, different isomers are going to come. Is it not? Right? Fine. Now that like that, how many isomers are possible is what they're asking. Right? And obviously, how will you do the reaction? You have to go for Cl2 in the presence of H nu, obviously. Right? So that you'll have again free radical mechanism here, but here it is going to be what kind of reaction this is, guys? This reaction,
Free radical addition.
Free radical addition. This is
Substitution.
Substitution. Sorry.
Yes, because now hydrogen is getting substituted with chlorine. Right? So this is a free radical substitution. Okay, fine. Now we'll check for the possibilities. Now the first possibility is that say we'll put 3 carbon atoms. Only forget about the hydrogens. Right? Now first possibility is that I can put, there are two chlorine atoms I got to account for. Say in the first carbon atom itself I'll put. That is one possibility. Second possibility is that say in the second carbon atom itself we'll put both chlorine atom. Third possibility is that I can put it in the third carbon atom itself the 2 chlorine atoms. Correct? Can I put the chlorine atom here again?
Sir, first and second.
Only first and second. Why cannot again write another structure with 2 Cls here?
So the naming
Sir,
is the same.
Exactly. This is how you avoid redundancy. That means how do you do if you how to avoid duplicates, right? It's better to give the name of the compounds, right? So you see that here it will be 1, 1 dichloro. Even if I put it here, again it is going to become 1, 1 dichloro only. Okay, so you'll not take that. Okay, fine. Next possibility is again I have 3 carbons. First and the second carbon I'll be able to put the chlorine, or I'll be able to put it in the first and the third carbon atom, or in the second and third carbon atom. Correct?
The second and third is the same.
Exactly. Second and third are going to be same as the first and the second one. Because again, if you start putting here and here, you'll put 1 here, 2 here again. Again, first and second carbon atom, only those are. That's it. These are the only possibilities. Right? How many possibilities now? 4. Right? 1, 2, 3, 4. Okay. Right. Next. Which of the following halogen exchange reaction will happen? Look at this. Right. So we have Ri and NaCl. Now, how do you predict whether this reaction will happen or not, guys?
Sir, the previous question I have a doubt.
Okay, please tell me.
Sir, what if we put 2 chlorine at the center? Then that's one possibility. Another 1 chlorine at first carbon and 1 chlorine at third carbon. That's second possibility. Then 1 chlorine at first carbon and second chlorine at second carbon. That's third possibility. Then
this one, both the chlorine atom in the first question itself.
Okay, sir.
Right? Yeah. Okay. Yeah. So yeah, how do you what is that? Understand whether this particular reactions can happen or not? First of all, before moving on to anything, what is the type of reaction of all of these?
Halogen exchange.
Okay. In general.
Substitution.
Substitution. What
So
substitution?
nucleophilic substitution.
Absolutely. Right. Now this is I minus, say I minus getting replaced with Cl minus, or Cl minus getting replaced with I minus, something like that. Is it not? Right. So you can easily see that. What is that? This is nothing but one nucleophile replacing another nucleophile. Right. So definitely it is going to be a nucleophilic substitution reaction. Okay. Right. Now, how again? Fine, understood. Right. Now, what you have to understand is, say I have RLG, that is, LG is a leaving group. Okay. And we have a nucleophile. Right. Now, for this reaction to happen, right, what is the condition? The condition is that the nucleophilicity, we call it. Okay. The nucleophilicity of the nucleophile, that is the incoming nucleophile, should be greater than the leaving group. That is what you have to understand. Now, when I say nucleophilicity, it is the reactivity. Okay, the ability for it to act as a nucleophile, how fast it can react, the reactivity. Okay, fine. So now this nucleophile, but how do you decide? Is another question. Okay, fine. Anyways, right. So now here, have you ever seen this reaction first of all anywhere? Ri plus NaCl. You wouldn't have seen. Okay. Rf plus KCl, again nothing. RCl plus NaI. This reaction you would have seen. What is the reaction called as?
Finkelstein.
Finkelstein.
Yes, this is what is called as your Finkelstein reaction. This you have seen for sure. Okay. Next, CH3F with AgBr. Have you seen?
Swartz.
No, that is CH3Br with your AgF will give you CH3F. Oh, but wait. So if you write CH3, Ball-Schemen is different. That is an amines. Okay, fine. If you have CH3Br and if you put AgF, now you are going to get CH3F. This is your Swartz. Right? When you form fluoride as the product, F, there should be RF in the product. That is Swartz. Okay? Right. Not the opposite way. Right? Here what is happening? Here F is getting replaced with Br. That is not the Swartz reaction. Right? The only correct answer is this, where your Cl is getting replaced with your iodine. Now remember this. Halogen exchange is possible for only the production of iodides, or sorry, alkyl iodides and alkyl fluids. Okay, it cannot be you will not be able to form RCl or RF from this. Sorry, not RF. You will not be able to form RCl and RBr from this. Okay, you can name if you want, you can take it here. RCl cannot be formed. What is wrong? Okay. RBr also cannot be formed. Only RF and RI can be formed. In case of your halogen exchange.
Sir, but in option A, chlorine is more electronegative, sir, according to the condition.
No, Kana, we are doing all this in aqueous solutions. Okay. In aqueous solution, Cl minus is going to be a weaker nucleophile when compared to I minus.
Okay, sir.
Okay. Right. That's why I didn't go into the details. Again, that is a very advanced topic. We don't have to go into deciding How do you say that this is going to be more reactive? How do you say this is going to be less reactive, or this is more nucleophilic? Less nucleophilic is again going to be 1 hour lecture.
Sir,
You don't know. Yeah.
sir, since iodine is a better leaving group, will that affect that?
That's also a good question, right? But again, leaving capacity is one criteria to look for. Absolutely. Right. But in aqueous solutions, your I minus being a better nucleophile than Cl minus will not be able to replace it. Okay. But yeah, what you're saying is absolutely true. I minus is a better leaving group. True. Right. But it's the opposite. That is, your Cl minus being a weaker nucleophile will not be able to replace this.
Okay. Sir.
Okay. Right. Fine. Next. Fluorobenzene, that is C6H5F, can be synthesized in the laboratory by what? Heating phenol with HF and KF. Have you ever seen this? No, you wouldn't have seen this. And no
No, sir.
reaction, right? By okay, what about the second one? By first from aniline diacerization followed by heating of diazonium salt with HbF4. Have you seen this? Have you seen this? I have aniline. Okay, now I'll go for NaNO2 plus HCl, right? So you will form N2 plus Cl minus. And if I went for HbF4 bar heating, you are going to convert this entire thing into F. Have you seen this?
Sandmeyer reactor.
Yes,
Yes.
sir.
This is not Sandmeyer's.
Balskimen.
This is Balskimen. Okay, this is your Balskimen reaction. Okay, this is the only method by which you'll be able to produce fluorobenzene. Okay, and again, the Sandmeyer's or your other Gattermann is the only way by which I'll be able to. No. Sandmeyer's and Gattermann is for chlorobenzene and fluorobenzene. Right now, the same thing from this diazonium salt. If I put Ki, right, then that is going to give me iodine. These two are the only ways for us to produce your fluorobenzene and iodobenzene. For chlorobenzene and fluorobenzene, we have enough methods, right? But for fluorine and iodine, from the diazonium salt is the only method. Okay, right. So that is the answer. B. This is your Balskimen reaction. Okay, moving on. Okay, when chlorine is passed through propene at 400 degrees Celsius, which is the product is formed? And that is very simple, right? So we have propene, C, double bond C. This is what the propene. Now we are adding chlorine. Chlorine is what? Not HCl, Cl2. Right? So what will happen? Again, addition reaction is going to happen. One chlorine here, another chlorine here. So you'll get CH3, CHCl, CH2Cl. Right? So what is the answer? What is the name of the compound? 1, 2, 3. 1, 2, dichloropropane. How is it? Ethane? No. Okay. PVC, polyvinyl. What?
Vinyl chloride.
Vinyl chloride.
No, it's not. Vinyl and allyl are different. I think this is a printing mistake, right? This is 1, 2 dichloropropane. That's the answer. Answer is D.
So then what is vinyl chloride?
Okay, vinyl chloride is this kind. Say if at all you have, say, you have a C double bond C, right? To directly to that double bond C, if you have a chloride attached, that is called vinyl chloride, right? But say I have a C double bond C, and to that a single bond carbon is attached, and to that the chlorine atom is attached. Now you see the chlorine is not directly attached to the C double bond C carbon, right? Now this particular group is what is called as your allyl group or allyl halide. Okay, vinyl is carbon atom that are directly attached to the double bond carbon, whereas in allyl it is not directly attached. In between the two, there is going to be one single bond carbon. Okay, right? The answer to the question is nothing matching. The answer is 1, 2 dichloropropane, not ethane. Okay, right. Next, moving on. Which of the following has the highest boiling point? Okay, for boiling point, what are the criteria? Quickly tell me.
Linear chain as I is boiled.
Fine. For before that,
Intermolecular hydrogen bonding.
Okay,
Greater the
fine.
molar mass, greater the.
Hydrogen bonding is the first criteria we will take, most important point. But none of these hydrogen bonding is going to be possible because all are chlorines. Only with alcohols, only with acids, amines, those things are possible. Okay, fine. So now next one is your someone said molar mass. Yes, that's the next criteria to look for. Obviously, in this
Surface area.
surface area is nothing but your branching, linear chain. Everything said. They said that it is going to be inversely proportional to branching. These are the points you will look for boiling point. Right? Boiling point is directly proportional to hydrogen bonding, directly proportional to the molecular mass of the compound, but inversely proportional to the branching. That is, a linear compound is going to have more boiling point. A branched compound is going to have lesser boiling point. Okay, right. Now you see that this is having 1, 2, 3, 3 carbon atoms only. This is having 1, 2, 3, 4. 4 carbon atoms that is having, right? Definitely this is not the answer. Then for this 1, 2, 3, 4, again 4 carbon atoms that is having. Now here 3 plus 1, again 4 carbon atoms is having. Right? But now you see this is heavily branched. How do you write this? CH3, C, CH3, one more CH3, and one more Br or Cl, whatever it is. Now this is heavily branched. Whereas in this case, how do you write this compound? Whenever you put something in brackets, that means it is a branch. Okay, but whereas you see this is the most linear structure with the same molecular formula, same molecular mass also. Right? So you will see that the answer is going to be B, because that is having the least amount of branching and the highest molecular mass. Right? Okay. Yeah. Moving on. I mean, which of the following has the highest melting point? Okay. In this case, I think just chlorobenzene.
Sir, why not
Sir.
benzene?
Yeah.
Sir, what is W dichlorobenzene?
Yeah, I think it's a printing mistake again. This is meta M. Meta dichlorobenzene is what it is. Okay, I think for melting point also, I think you have to follow the same thing, right? More the molecular mass and stuff like that, that's the same thing you'll look for. But I think there's going to be one more criteria, that is dipole moment.
Sir, is it para-dichlorobenzene?
Yeah, definitely. Yeah, because para-dichlorobenzene is going to be, say, what you understand is, right? We have this Cl like this, right? And we have this Cl like this. Okay. Now you see that this is going to have a partial negative charge, this is going to have a partial positive charge, and this chlorine will be able to attract this one, right? And you have a partial negative on this. This chlorine will be able to attract this carbon. Same happens with this. You will see that there'll be a del plus and del minus. There'll be a del minus and del plus. Again, del plus del minus, del plus del minus. Okay, now this will be able to perfectly do this. Orthogonal is, it can happen. It's not like it's not happen, but it will be maximum efficient in the case of your para-dichlorobenzene only, because it is going to be exactly symmetric, right? So that is going to have the strongest of intermolecular forces, right? So definitely it is going to be having the highest melting point. Okay, right. Next, which of the following are arranged in the decreasing order of dipole moment? Okay. Now dipole moment, how do you do? Right? Do you know how do you dipole moments? What is dipole moment? No? Okay. Just give me a time. Just give me a minute. Just drink water. Give me 1 second. Okay, fine. So the question is, do the following are arranged in the increasing order or decreasing or decreasing order of dipole moment? Doesn't matter. So what is dipole moment? Right? Dipole, first of all, what do you mean by this term dipole? Dipole is nothing but equal and opposite charges separated by a distance. This is the exact definition of what a dipole is. We'll see what a dipole moment later. Okay, a dipole is something which is going to be an arrangement where I'm going to have an equal and an opposite charge separated by some amount of distance. Okay, right. Now, how is it going to be? It's going to be like this. For example, say one is having plus Q charge, right? And in some distance away, you need to have a minus Q charge. Let me write it like this. This is some plus Q and this is some minus Q, right? And in between these two, there has to be some distance. This entire arrangement is what is called as your dipole. Okay, this entire arrangement is what is called as your dipole. Okay, now this is going to have a physical quantity called as dipole moment. Okay, now that dipole moment is denoted by letter mu and it's a vector quantity, right, which is equal to Q into D. That is, if you look at the arrangement, whatever is the charge value into the distance of the separation, what is the distance between these two, right? That product is nothing but your dipole moment, right? Now, what should be the direction? We said it's a vector, so definitely this is the magnitude, right? What should be the direction is again the question, right? Now, direction is towards more electronegative element. Right? So the direction is going to be towards your more electronegative element. All right. So now, for example, if you have, say, an example of for a CCl bond, and say other things are there, other three bonds are there, don't worry about it. Okay. Now you see that this is going to have a partial negative charge. Again, we have already spoke about this, and this is going to have a partial positive charge. We already spoken about this, right? Now, what will happen is that this is going to act as a dipole, right? This particular bond is going to act as a dipole, is it not? Again, I have a plus Q, minus Q, separated by some distance, that is your bond length between the carbon and chlorine, right? That is nothing but a dipole, right? So obviously, all the dipoles will have some dipole moment. What will be the value? That mu will be equal to the del value, whatever is the positive or the negative of the magnitude, into the bond length of CCl bond, right? That is how you see this, right? Fine. Now what will be the direction? This is the magnitude. That's okay. Now what will be the direction? It is going to be towards the more electronegative atom. So can I say that this is the direction of your mu? Why? Because chlorine is more electronegative, right? Okay.
Yes.
Now going back to the question, right? Now they're asking about decreasing order. Now all things are same. CH3, CH3, CH3 everywhere is same. All that we have is CBr bond, we have CCl bond, and we have a CF bond. Right. Now, if I want to, everything is going to have a del plus del minus del plus del minus del plus del minus, everything is going to have, I mean, everything will be towards Br, towards chlorine, towards fluorine. That is what is going to be the direction of the dipole moments also, because that is only more electronegative. That's okay. But how do you compare them? How do you compare? This is going to have more dipole moment, this is going to have less dipole moment. Obviously, depending on this formula, that is the charge into the distance. Bond length is not going to be much of a criteria, but this one, the amount of charge is definitely going to matter a lot. Okay, right. So in that case, tell me, say if I say that this is del 1 plus, this is del 2 plus on this carbon, and del 3 plus on this carbon, and here also del 1 negative, del 2 negative, del 3 negative. Okay, now tell me which will be the greatest value among these dels? Del 1, del 2,
Del
or
3 plus.
obviously, because fluorine is the most electronegative one, right? That is going to pull the electron towards it so much so that the amount of charge produced on carbon is maximum in case of the CF bond, right? So the CF bond should have the highest this thing, What is that?
Sir,
Yeah.
sir, so the question should have been increasing, right? Because none of the options match.
Mhm.
Sir, but I also have a doubt.
Mhm.
Sir, if we consider the distance, fluorine as the smallest compared to
Yes,
chlorine and
yes,
bromine.
yes.
So in dipole moment, we also use the distance thing, right?
Definitely. Coming. So the probable answer is B. Right? We'll see how it is. Okay. Yeah. See, look at this question, guys. Very interesting. So now this thing definitely is going to be based on charge. Now, based on charge, who's the winner? CF is the winner. Okay. But if I look at the other criteria, that is your bond length between your C and X, in this case, it is C and L, sorry, C and Cl, in general is going to be with respect to C and X. Right. Now, what happened to whatever I wrote? Okay. Fine. Right. So now you see that this CF bond will be the smallest bond or the shortest bond, and CBr bond is going to be the longest bond because bromine atom is the biggest and fluorine atom is the smallest. Right. So obviously here the winner, if I use the length criteria, CBr is coming out to be the winner. Right. But even though in both the cases chlorine is not the winner, but both the things actually somehow enhance the dipole moment of CCl because the amount of charge is good enough, right? And the length is also quite larger, right? So actually the first the maximum dipole moment is going to be there for the CCl bond. What is wrong? CCl bond is going to the maximum. Then obviously the first priority has to be given to the del, the amount of charge. So then comes your CF bond, and then the least, even though the bond length is going to be the higher, as I said, the most dominating factor is going to be del, right? So then comes your CBr bond. Okay, so this is definitely the answer for the question. Okay, right.
Sir, I have a doubt.
Yes, please.
Can we take even electronegativity as a criteria, sir? Because chlorine has more electronegativity than fluorine.
No. Fluorine is more electronegative, right?
Sir, no, sir. I think chlorine, I think, sir.
Hey, fluorine is the most electronegative element. Okay?
Okay.
Right. Okay, I think the same question this is, right? Don't worry about this. Next. Right. Explain why alkyl halides are generally not prepared in the laboratory by free radical halogenation of alkanes. Why is it like this? That means that what they're asking is, say for example, if I had CH4, if I put chlorine in the presence of H nu, I am going to have CH3Cl, for example, one hydrogen atom getting replaced with one chlorine atom. That's what is happening. Alkanes. Free radical halogenation of alkanes is this only. Okay, this is again a free radical substitution reaction. H dot is replaced with your Cl dot.
Sir.
Yes.
Sir, like this reaction will continue and chloroform will be formed.
Yeah. Chloroform CCl4 carbon tetrachloride that can also be formed. Absolutely, yes. Right.
So like, isn't that the answer?
No. Explain why alkyl halides are not prepared by this reaction is a very different thing because this is explosive. This is a very violent reaction.
Sir,
Yeah.
sir, I have an answer different.
Yeah, tell me.
Sir, since according to Suprajit, chloroform will be formed, right?
Mhm.
So when it comes in contact with oxygen and light, it forms a poison which is poisonous and hence not suitable for.
Mhm. That's good. Like say, telling that chloroform and when it comes in contact with oxygen and light, right?
Yes, sir.
Oxygen and light forms phosgene.
Phosgene, which is
That is
poisonous.
poison. Good.
Sir,
Like
I think that is the answer given in NCRT because this is a reason question.
oh, that's okay. Then that's good. Then we'll take it. Right. That's a good answer also. Right. So you see that what they're trying to say, we'll just sum up everything here. Okay, this reaction is fine only. No issue. Okay, right? So what they're trying to say is that this CH4, if it reacts Cl2 in the presence of H nu, you will form CH3Cl, and one more Cl2 in the presence of H nu, you will form CH2Cl2, and one more Cl2 bar H nu, you are going to form CH3, sorry, CHCl3, and one more Cl2 in the presence of H nu, you are going to form CCl4, right? And the dangerous compound here is this CHCl3. Now, what is going to happen? This CHCl3 is going to react with O2 and light to form phosgene. I think phosgene is C double bond O with
POCl.
ClCl, right?
Yes, sir.
Ah, correct. Right? C double bond O with ClCl. This is what is called as phosgene. Okay, H is not there. Okay, I'll write it somewhere here. Phosgene. Okay, now this is the poisonous gas. Okay, and if we inhale it, it's very dangerous for us. Okay, that's the reason why we are not doing it. That's good. That's good. Okay. Right. Moving on. Okay. Explain why chlorination of N-butane in the presence of light at 200 Kelvin gives a mixture of 72% 2-chlorobutane and 28% 1-chlorobutane. Now look at this. CH3N butane you're going to take. Right. Now they're telling that if I go for Cl2 bar H nu, monochlorination, only one Cl will replace. And the possibilities are CH, Cl, CH2, Cl. This is your 2-chloro. Right. And the next one is in the first carbon atom itself. CH2Cl, CH2, CH2, CH3. This is your 1-chloro. Okay. Now they are telling that 78% of 2-chloro and around 22% of 72 and 28, whatever it is. 72 and 28% of 2-chloro and 1-chloro respectively are forming. They're asking me to explain why is it like this. What is the mechanism here?
Free radical substitution.
Free radical substitution this is. So now what you understand is that this, before this would have been chlorine would have been attacked, this would have been the free radical. And before this chlorine would have attacked, this would have been the free radical. Is it not? So definitely what you have to say, secondary free radical is formed here, primary free radical is formed here. Definitely secondary free radical is more stable than the primary free radical. And so you say that 2-chlorobutane will be formed in major amount compared to 1-chlorobutane because of the stability of the free radical. Okay. Right. Fine. Next. Which reaction fails in the case of what? I think it's in case of the tertiary alkyl halides. I don't know what this question is. Okay. I will maybe come back tomorrow. I'll ask them what is this question. I didn't prepare this. Okay.
Sir?
Yeah, tell me.
Is it instead of sodium, it's iron and tertiary alkyl halide?
No. That doesn't make sense at all.
Okay.
Okay. Fine. Next question. Explain the following in 1 or 2 sentences. Right. Displacement of cyanide and amide ion is never observed in nucleophilic substitution reactions. That is, have you ever seen RCN getting replaced with another nucleophile? What is amide? Amide is RNH2. Sorry. Amide is RCONH2. Okay, RCONH2. And again, nucleophile, if you're going to attack again, so you see that this kind of nucleophile is happening or not. This is not going to happen. They're asking you why. Now, please understand, people. The reactivity, what obviously is the nucleophilic substitution reaction, the reactivity is directly proportional to the leaving capacity. I'll write somewhere next page. The reactivity is directly proportional to the leaving capacity of the leaving group of the Lg. That means if I have an RLG, a nucleophile like this, and that is going to form RNU, plus the leaving group is going to go out. Leaving group is the going out group, right? So more and more this reaction is going to happen if more and more leaving capacity this leaving group has. More and more easily it can leave, right? So now how do you compare the leaving capacities? Leaving capacity is inversely proportional to the basic strength. Okay, leaving capacity is inversely proportional to the basic strength. Right? That means stronger bases, very strong bases are very bad leaving groups, whereas very weak bases are going to be very good leaving groups. Okay, weak bases are good leaving groups, and strong bases are very bad leaving groups. Okay, right. Now, what do you understand is that, for example, you have this Cn minus has to leave, right? In the previous section, you want to make sure that the Cn minus leaves and the nucleophile comes in attack. Right. Now, this Cn minus is going to be a very strong base. Okay. And even your C double bond O NH2 minus is also going to be a very strong base. Right. So you have to write a sentence like this. The amide ion and the cyanide ion are very bad leaving groups because they are very strong bases. And that's why this reaction doesn't happen. Okay. Right. These two are very strong bases. That's why the leaving capacity is very, very small. And so they cannot undergo any kind of nucleophilic substitutions. Okay. Right. Next.
Sir?
Yeah.
Sir, along with this, can we say like in cyanide, the RC, that bond is more stable due to same electronegativities of the carbon?
Oh, no. First of all, that's a very wrong statement. The bond might be strong. Okay. But it is because of the same electronegativity? No. First of all, if you have, for example, say CH3C triple bond N, this carbon atom is sp3 hybridized and this carbon atom is sp hybridized. Okay, right? There is a huge difference in hybridization, and so there is going to be some electronegativity difference, and that is why the bond is stronger. Okay, when you have almost same electronegativity, the bond is not that strong. Whereas when you have huge difference in electronegativity, then the bond is stronger, right? So sp hybridized carbon atom is more electronegative. sp3 hybridized carbon atom is less electronegative. Right? So definitely that bond is stronger. Yeah. But the better way to speak only is in terms of your leaving capacity. That's the best way to answer.
Sir, you're saying like more the difference in electronegativity, the bond is
stronger.
Sir, then like if you consider KCN, which is ionic in nature, sir. So in aqueous, it will exist as K plus and Cn minus, right?
Okay.
So,
oh, that is because that we are talking only about covalent bonds here. Right? The very nature of ionic bond is that there is no particular bond there, right? It is an ionic bond. It is just an electrostatic force of attraction. Right? But say if at all I want to compare say HF bond strength with HCl bond strength, HF bond is definitely going to be a stronger bond because of high difference electronegativity.
Okay, sir.
Okay. But if you go for ionic compound, that's an entirely different story. Okay.
Yes, sir.
Right. Next. Next question is RCl is hydrolyzed to ROH slowly, but the reaction is rapid if a catalytic amount of Ki is added to the solution. Right? What they're trying to say? RCl is hydrolyzed to ROH slowly. That means they're talking about RCl is okay, I think it's ROH or RCl. Yeah. RCl is hydrolyzed to ROH. Hydrolyzed means we are going for H2O in the presence of H plus. Okay. Now they're writing that this reaction is quite slow. Right. But if I have RCl, when I go for hydrolysis, if I do this in the presence of Ki, this ROH formed, this reaction becomes little faster. Right? Why is what they're asking. Okay. Now,
sir, Ki is a catalyst.
K is a catalyst. Yes.
Sir, so in the presence of catalyst, obviously the reaction will be faster.
Why? Why especially K? What is the role of K? How K is able to make sure the reaction is becoming faster?
Sir, it
Sir,
obstructs
Ki
the
would,
chlorine.
yes, sir, it would break the chlorine and alkyl bond.
Yes. So basically, the first step in this case is that you are going to form Ri. This and this are going to react, and you are going to form Ri. And now this reaction becomes very easy. Why this reaction becomes very easy?
Iodine is a better leaving group.
Absolutely. Right. Once you convert this into Ri, I minus is a very good leaving group, then the hydrolysis becomes very easy. This is how you must write. Right? You must write RCl reacts with Ki to form Ri. Right? Whereas in that the I minus is a very good leaving group. Now the hydrolysis becomes more efficient or more feasible because of I minus being a better leaving group than Cl minus. In this case, it is slow because Cl minus is going to be a little bad leaving group compared to I minus for sure. Right? Okay, fine. I think, guys, this is going to be the last question. I'm not feeling that good. Okay, maybe we'll continue tomorrow, or you can go through the question and ask me the question in the tomorrow's class. Okay, there are only going to be some 20 more questions. Easily you can answer this. Okay, fine. So this one, I have HBr in the presence of peroxide. You know, it is going to give me anti-Markovnikov addition. That is CH3, CH2, CH2Br. And then we are going for NaI in the acetone. Now what is going to happen? This is now if I go for NaI in the acetone, that Br minus is going to get replaced with your I. Yeah, NaI will give you I. That's it, right? You're telling you have to complete the final reaction, you have to find out X and Y, or you have to convert this one. You have to convert propene to 1 iodopropane. Okay, same thing, right? Propene is this. We start with this, right? Now you can go for Y, that is nothing but a 1 iodopropane. This is how you go for the conversion. You first go for HO peroxide, you go for anti-Markovnikov addition, and then convert it into iodide by your Schwarz reaction. No, sorry, Finkelstein reaction. Okay, right? Okay, thank you so much. Like there are only going to be 15 more questions, I guess. Not much questions are going to be there, right? You can ask me a doubt.
Sir, I have a doubt, sir.
Yes.
Sir, in general case, can we say that is stability inversely proportional to reactivity?
Yeah, we can say that.
Okay.
Right, but we are talking. If you talk about the stability of the reactant, yes. But if you talk about the stability of the intermediate, that is carbocation or carbon is getting formed, there more is reactivity.
Yes, sir.
Right. Okay, guys. Thank you so much. We'll meet again tomorrow.
Yes, yes, yes.
Thank you.
Thank you, sir.
Thank you.
Sir,
Thank you, sir.
sir,
So,
Yes.
sir, we'll be continuing tomorrow from these questions, right?
Yeah, that's what. But by this time, you just go through all the questions. If you have any doubts, you can go. You can ask me the questions.
Okay, sir.
Okay. Cool. Thank you.
Thank you, sir.
Thank you.